Hello, my name is Sean Allman. The title of my project is called Salt Ion Removal from a Brine Solution. My mentor's name is Dr. Salim Azouz. The goal of this project is to design a low energy consuming and mechanically driven machine to separate sodium and chloride ions from a brine solution using an electric field across a flowing seawater channel. The motivation for this research is that due to the rapid increase in the world's population, coupled with changes in climate, results in a growing strain on existing freshwater supplies needed. Currently, there are 663 million people worldwide that do not have access to safe, clean drinking water. Figure 1 is a map that shows the depletion of water across the world. The red areas use more water per year than they receive. So where is all the water? Well, Figure 2 is an illustration of how much fresh water is available. Of all the water on Earth, 97.4% of it is salt water. So that leaves only 2.6% to be fresh water. Of that 2.6%, 72.5% of that water is frozen, 28.15% is groundwater, and the rest, which is only 0.3%, is fresh surface water. The technology that we're utilizing to perform this research is capacitive deionization. Now, capacitive deionization is an electroabsorption method using a combination of an absorption media and an electrical field to separate ions and charged particles. Anions, which are ions with a negative charge, are removed from the water and are attracted to the positively polarized electrode. Likewise, cations, which are positively charged, are attracted to the cathode, which is the negatively charged electrode. Now, there are several advantages of capacitive deionization, one being that it's scalable, it's also simple to operate, and it's low energy consumption. Figure 3 illustrates an example of capacitive deionization. In the top image, the electrodes are charged, and therefore the ions inside the water are attracted to the electrodes. In the bottom image, the electrodes are de-energized, which means they release the ions back into the water. So for Figure 4, we have our model apparatus. This is a two-channel model where water flows from the top left to the bottom right, while an electrified turbine grabs the ions and then de-energizes itself and drops them into the waste channel as the turbine spins. This semester, we did a lot of testing, and here are our results. First, newly coated electrodes are able to withstand very high and wide-ranging voltage, but they would not attract ions as expected during experimentation. We also performed conductivity tests on many various saltwater concentrations that utilize voltages ranging from 100 volts to 1000 volts. Then we attempted tests using the Van de Graaff generator with voltages of up to 1,000,000 volts. Now at this stage of the project, it was determined that there's no correlation between a change in conductivity and voltage levels of electrodes. We believe that the lack of obtaining tangible conductivity results is due to the electroneutrality principle of chemical solutions. Therefore, future work consists of utilizing a sodium electrode to measure ions directly. This should bypass the electroneutrality principle and allow us to see if the ions are truly attracted to the high voltage electrodes. Thank you for listening. I hope you enjoyed this research.